Hi, welcome back. We have one more lesson in this first unit of our data structures and algorithms course. Today I want to talk about searches. The linear search should be a review, and to some extent so should binary search. But let's make sure we go over them. I want you to download the viewers from my webpage. You can access them right here. They are linear search viewer and binary search viewer. And I want us to pay attention to how many comparisons they require. So let's go ahead and take a look at the linear search viewer first. And what this application is going to allow us to do, we're going to generate a random list of 16 numbers. Okay, so the random list here, when we enter a value to be searched for, such as like 92, what's going to happen is we're going to start right here and we're going to just iterate from left to right until we find the first value that is equal to 92. If there's another 92, it won't tell us that there were two of them. We basically wrote this exact method when we did the index of. And you can see index of 4, and it had 5 comparisons. All right, let's try another one. Let's try 81. Okay, it found it at the 12th and had 13 comparisons. Let's do 89. That one it just found at index 0, it just found the very first comparison. It saw that it was equal to our target, and we were done. Notice it did not note that there was a second 89. We'd have to search from the back. We could do like a last index of, and that is a reasonable method to have. So you can see that if we're looking for the value that's at the very front of the array, it could have a one comparison thing. But if I look for something at the end of the array, it's going to take the entire length. You can see it going all the way through. Oh, but there was a 17 there. I didn't even notice it. We could look at a 78. I think there's only one of those. And you can see it pretty much traverses the entire array there. So on average, it's going to take half the array positions. Sometimes it'll be a little less than half. Sometimes it'll be a little more than half. Worst case scenario, you'd have to look through the entire array. Best case scenario, only at the front. But on average, it's going to take for in data items in the array in over 2. But when we're talking about big O, that over 2, we just throw it away, right? So the big O notation for this linear search is O in. Now, that would be a superhuman fast sort, an impossibly fast sort, but that is a very, very slow search. That means that you're basically having to go through the entire thing. And if you're talking about millions of customers in an online store's database, or even millions upon millions of them, that gets pretty slow, especially if you do it over and over and over again. So next, I want to look at, again, look at those comparison numbers, 15. I want to look at the binary search viewer. Now, the binary search does have a precondition that we're going to have to meet, and that is that the array has to be sorted. The algorithm does not work or guarantee any kind of working when the array is not sorted. So before I can do this, I need to sort this, and that takes, at best, if we're using like a merge sort or a quick sort, in log n. So that is an in times log n is greater than just in. So having to sort it is already taking me more time than it would to just perform a linear search. Let's search for the number 77. Let's see what happens. Okay, so moving pretty quickly. We could probably turn down the speed in the if you go here in the binary search viewer, but I wanted you to notice how that worked. Note it only had 3 comparisons. The first thing that happened was it went right in the middle at the 53 and it highlighted that side. From there, it realized that it then checked the middle value again, which I think was the 81. And I want you to watch it happen. Let me have it search again. Watch how it isolates and zeroes in over. It starts with the whole thing, then half, then half. It's cutting down the possibilities by half. So first it was this whole array. It then realized that it would only have to be the part from 53 over. It then checked halfway through there and found that it'd have to be something from 81 less. Remember, it's looking for 77. It then checked the 62, probably the 54, and then said, oh, it's got to be the 62 or greater, in which case it found the 77. It took 3 comparisons. Let's try 98. That's that last element. That took 16 comparisons on the last one, or at least it would have. We found it in 4. Let's try like 100. What happens if I search for 100? It's just going to say it's not there. Okay. But it only took it 4 comparisons. I guess I didn't write it to return. It should return -1. but let's try 26. 2 comparisons. And index 0, 1, 2, 3. Okay, let's try number 8. Found it in 4 comparisons. So as we do this, sometimes we can get lucky and get on the very first value or even on like a couple of them. Sometimes it takes quite a bit of time, but it's not going to be more than 5 comparisons. That's never going to happen. And that's because there's 16 items in here and we're splitting it in half every single time. So at worst, we'd have to do that 4 times because 2 to the 4th power is 16. Or in other words, log base 2, since we're splitting in half, base 2 of 16 is 4. And then I have that one extra comparison to get it right the first time. Let's try another one. I'll generate some random numbers. Let's try the 30. Got it in 3. What does it search for? It's the 84. Okay, what if I tell it 84? Oops, I don't think I sorted the numbers. Okay, let's try that again. How did that even work? 39. Let's search that one. Got it in 3. It's starting with the 51. So if I tell it 51, we ought to get it in 1 comparison. Yeah. And what happens if I do like 41? Let's try that. Yeah, that's the 5. That's the worst one it could be. But that's monumentally faster, isn't it? So you have to sort it first. But then once you sort it, it's log in. We're talking about, if you got 1 million items in the list, the log of 1 million, well, in base 10, log of 1 million is 6. That it'll be a little bit more in base 2, but still a very small number, less smaller than 1 million. So this begs the question, should you sort and then search? Well, the sort is in log in, right? And then you got to search after that, which is just log in. Well, this is already longer than that. If I take it out of the logs, I would really need to have like parameters here for what that could be. But let's just say that this is approximately in log in when I remove it from the big O plus log in. And I can factor out a log in and I get n plus 1. And then big O, that's just an n. So it's interesting to note that, in fact, it turns out that sorting and then searching is really no longer than just sorting. So it's like if you sort something, you get to search it for free, which is kind of cool, I guess. But if you were going to be doing something over and over and over again, if you know you're going to have to search something time and time and time again, doesn't it make sense to sort it? I mean, I think of my record collection at home. I mean, if I'm going to listen to my records quite often, I want to be able to find the record I want. I might sort them alphabetically. I might sort them by genre, but I'm going to have some sort of organization so I can find it. If there was someone who never listened to records, well, why would I care to sort them? I'll just go. It's going to take me more time to sort them. I mean, think about it. All the effort you got to go through to sort. And I mean, you know how long it takes to alphabetize something, right? But if you're just going to look for one record, you want to listen to that one time, well, then you don't need to sort it. But if you know you're going to, over time, have to do it a lot, you should probably sort it because it will save you time in the long run. Okay, so let's code it. All right, I went ahead and put in a class called searches. I went ahead and put in the 3 methods we're going to be using today. This is just a utility class, so they are static, so you can call them directly on the class searches. I went ahead and had each one of them return -1 because I got to return something or they'll have an error. So we're going to start with these 2, and then we're going to throw in the recursion. Okay, so let's start with the linear search. The linear search just starts at index 0, returns the index of the first time it finds the target. Keep in mind you could do a linear search with an array list or an array, because a list backed by an array is an array. So you'd have the same big O, same kind of stuff. Be using .get instead of bracket. So why don't you pause the video right now and write the linear search? Should be a nice little review. We'll go over it. Okay, let's see how you did. I'm just going to do a simple for loop. Start at 0. I'm going to loop through r.length. If r bracket I is equal to the target, then what I'm going to do is I'm going to return that I because I have found the index. Now, don't do the thing where you say else return -1 here. That would return -1 every time except for when the very first item was it. Don't do that. You need to wait until you're done searching the entire array before you can return -1. All right, that's going to work. We can compile it because I made these return -1s. If you want to just test it out, just going to, right here on my little workbench, my little interactive shell, just type in some numbers here, 5, 9. I'm going to use this array a lot, so I'm going to, linear search does not care if it's sorted, but I want to make it sorted so I can use it for something else. All right, I think that's good enough. And then if I type in, oh, my virtual machine was being a little wonky. There it goes. Bring that over here. Oh, bring it over. Okay. Now I can call on searches because they're static. You see they're right here. I can just say we just wrote the linear search, right? So click that array. Let's search for 101. It's index 5. 0, 1, 2, 3, 4, 5. Looks good. Let's do another one. We're going to do that array, and we're going to search for 100. -1, because it's not there. Okay, cool. All right, next we're going to do the binary search. The process of binary search is you're going to create some variables. You're going to create a variable for let's go to the drawing board. I want you to get this. I want you to be able to write this search. I think you can do this. I believe in you. All right, we're gonna have a sorted array. Okay, so I think I'm just gonna draw the array with these little lines here. Okay, just imagine 3, 4, 5, 6, 7, 8. All right, so what I need to do is I need to make a variable for the front. Okay, so we'll make a front, and we'll make that 0, and then we need a back. And we want this back to be, if this is array R, we need that to be r.length -1. You could use r.length and make the back be not part of the partition that you're dealing with because we'll be partitioning. But then you really got to be careful how you calculate the mid. And it has some issues. So for this algorithm, it's definitely best to do that. Okay? So what's going to happen is we're going to start, I'll just label it F. And I'll call this back. We're going to start here and here. And we're going to be looking for a specific value. And let's say we're looking for the value, some target of 7. Well, what I want you to do is I want you to calculate this middle number. Well, this is 0, 1, 2, 3, 4, 5, 6, 7. Let's add 0 and 7 together. You get 7 divided by 2, you get 3, right? So 0, 1, 2, 3. So what's going to happen is we're going to reveal this. Okay, we're gonna reveal that, and three things can happen. If it's a 7, hurrah! That calculation we did is the right answer. Okay, which I'll go ahead and call that a mid. You're gonna need to calculate a mid at some point. Okay, if this value turns out to be something like I don't know, like a 12, then we know that this because it's sorted and we're looking for a 7 and we found this to be 12, we know that 7 has got to be somewhere to the left, right? So what we're going to do is we're going to make, because that was our mid, we're going to make our back change to there, okay? And then we're just going to repeat the process, right? Now, had it been something small like a 2, let's say we checked that value and it turned out to be smaller than the target, like I said, like a 2. Well, then in that case, we know that instead of going to the left from there, we need to go to the right. We need to go to the right. So we're going to go this way, which means I'm going to leave back here, and I'm going to move front here. And basically, we're just going to keep doing that until we find it. But as you know, how are we going to know when we didn't find it? Well, the way you're going to know that you didn't find it, when you're going to stop doing this procedure, this loop, is let's say you had front here at index, what is that? Index 4, 0, 1, 2, 3, 4. And you had back at index 4 as well, okay? So if I add 4 plus 4, I get 8. And if I divide that by 2, I'll get 4. So that's going to tell me mid. My mid's going to be the same as well, okay? And I open it up and I find out that what's there is actually an 8, all right? Well, because 7, my target, is less than that, that tells me that the target I'm looking for in my array has got to be to the left, which means that, as we saw earlier, keep front where it is and move backwards to this -1. Well, look what's happened. Now back is behind front, right? let's take a look. What about it the other way? What about if I got front and back the same index, so the mid ends up being the same index, the average of this two, but this time I look at it, it's a 6. Well, now I know, okay, well 7 must be that way, so that means back stays the same and front moves up. But now again, back is to the left of front, so that's when you know they stop. So use a while loop. Okay, give it your best shot. Give it a try. Then we'll go over it. Okay, so code it right now in binary search. Okay, let's see how you did. So what you want to do is you want to make your front start at 0, and your back, it needs to start at the array.length -1. That's really important. I've been playing with it, and it just doesn't really work very well. You have to do some extra stuff to fix it if you don't have back in that array. And what I'm going to do is I'm going to say while front is less than or equal to back. Or you could say while not front greater than back, or not back less than front, something like that. But we're going to keep doing this as long as front is less than or equal. Remember, they can line up perfectly, okay? And in fact, we need them to be able to do that. I'm going to calculate a mid. My mid is going to be front plus back divided by 2. And then I'll say if array bracket mid is less than the target. So what that means is that we have calculated a middle value, and that middle value, like say here we had this array, if I said my mid was 5 and I was looking for 7, that means I need to go to the right. That means I need to have my front become my mid plus 1, because I have gone too far. Not too far, but I have not gone. I know that I have to go to the right hand side. So if R bracket mid is less than your target, then your target must be on the other half of the array. So move your front past your mid. Else, if R bracket mid is greater than the target, well then that means that I must have gone, or I must have a middle value that is too big, right? So again, if let's say I pick 5 and my target was a 3, then that tells me if my middle value is bigger than what I'm looking for, it must be on the left-hand side. So I got to go on the left-hand side, which means I got to move my back to mid -1. And then lastly, what is else? Well, I've already handled when you're less than. I've handled when you're greater than. So this must be when you're equal, in which case you're just going to return mid. That's the index that we're looking for. Not sure whether those are getting all cattywampus. All right, let's run this again with, let's run this search here with this array. Okay, and I'll do a binary search, and I'll look for 313, which you can see is at index 6. Let's do another one. How about, let's look for the end. That's always a good one to make sure that's yours, because sometimes weird stuff happens there. And that's index 8. Good. Let's look for one that's not there. Let's try 1000. And good. All right, so I'm feeling good about that one. All right, next what we're going to do is we're going to write this recursively. Okay, let's do this one together, because we haven't done a lot of recursion yet. And basically, I want you to see it's the same thing. Sometimes recursion is useful to do. I actually did it with the algorithm because it allows me to pause it and animate it. So in my binary search viewer, I actually do a kind of a modified recursive version of it. So it is a good technique. But that being said, typically in this class, we're going to take recursion and try and take it out of recursion and put it back into iterative. So this is iterative. But we're going to try and do it recursively. So I've got an array. It's going to take in. We probably have some other method. This would probably be private. We have another method called this, but so it's going to take in an array, a beginning index, an ending index, and the target we're looking for. So here's what I'm going to say: if begin. Well, earlier we were using front and back. Let's use front and back. Let's change this. Let's change this. Be consistent, right? So if front is greater than back, that's the opposite of this statement here. That means I don't want to keep going. That's how I'm going to stop my recursion. I'm going to return -1 in that situation. That's because that's too far. Okay? too far down the rabbit hole. Okay, we kept going, 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 and we kept, we started with the array like this, and we went half, then we went half, then we went half, and then somehow they crisscrossed. All right, so I could say else, but I actually don't have to since I used the word return. If we didn't return, then everything else is what's going to happen. So what I'm going to do is look at three different ways this could be. If first we got to calculate the mid. Well, I'm getting ahead of myself. Let's make a mid. Mid is going to be front plus back divided by 2. If our bracket mid is less than the target, that means the target we've got a middle value of like 10. The target's 24. That means we need to go to the right. We need to keep searching to the right. Then what I'm going to do is I'm going to return what would be returned from calling binary search with this array with a front value of mid plus 1, the same back value, and the same target. So this becomes front because when I call this array, this is going to go in the front. So if I didn't find it this time, I recursively call it, and let's say it finds it at index 3. Then that recursive call will return that 3 back to right here, which will then return. So it could even be 4 or 5 layers, say return, 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 but eventually we'll get it back. All right, else if our bracket mid is greater than the target, then we must go to the left. So let's recur on the left. Binary search recursion array. I'm going to keep front the same, but back is going to become mid minus 1. And I'll keep the target the same. Lastly, if neither of those things happen, we must have found our lucky number. Let's return mid, which again might be returned to a previous call, to a previous call, to a previous call. But that's how it's going to be. Okay, so that should cover it. Let's try that out and just see if we got a good recursive algorithm. Okay, so I'm going to call binary search recursion. Give it this array. The front index is 0. The back index, this is 0, 1, 2, 3, 4, 5, 6, 7, 8 is the last index. We'll give it like 313. Cool. And let's make it search for something that doesn't work. So array, 0, what was it, 8, and then how about 100? -1. Okay, so there it is. In this lesson, we learned we reviewed a linear search, we talked about binary search iteratively, and we talked about binary search recursively. I like to have the back actually in the array. If you don't, you have to do some kind of fancy math footwork and like subtract a 1 or something like that. But the important thing again here is the process. So linear search, O(n), binary search, log(n). Those are the log(n) is a very fast search, right? Keep in mind that sorting, as the old saying goes, a super slow search would be an incredibly fast sort. Sorts are always slower. They're always at least in log(n), unless it's like a random best case scenario, but they're always at least in log(n), or if they're not good searches, not good sorts, they're in squared. Searches can't be longer than n. Even the most rudimentary linear search where you go through each and every item cannot be longer than n. But if we use a binary search, we can make it log(n). So with that in mind, I will see you in Unit 2 of Data Structures and Algorithms.